Kinetic-Molecular Theory and Intermolecular Forces, or KMT and IMFs. Chapter 13 to 2010, Mr. Nelson. States of matter. The fundamental difference between states of matter is the distance between particles. The states of matter. The state a substance is in at a particular temperature and pressure depends on two variables: the kinetic energy of the particles, the strength of the attractions between the particles, solid, liquid, gas, container, compress, flow, diffusion. Kinetic-Molecular Theory. A model that aids in our understanding of how gas particles behave and respond to changes. Theory of KMT. Gases consist of large numbers of molecules that are in continuous, random motion. Most molecules. Nobles, atoms. Theory of KMT. Total volume of all the molecules of the gas is negligible relative to the total volume in which the gas is contained. Theory of KMT. Attractive and repulsive forces between gas molecules are negligible. Theory of KMT. Energy can be transferred between molecules during collisions. Elastic collisions. The average kinetic energy of the molecules does not change with time. Theory of KMT. The average kinetic energy of the molecules is proportional to the absolute temperature. Effusion, diffusion through a hole. Effusion is the escape of gas molecules through a tiny hole into an evacuated space. Effusion. Let's compare effusion for helium and nitrogen. Helium, 4 grams per mole. N2, 28 grams per mole. With a lower mass, the helium balloon would deflate faster. Graham's law: Ke1 Ke2 equals half m1 v12 half m2 v22 equals m1 m2 v22 v12 m1. Intermolecular forces, IMFs. IMFs are found between molecules, not between the atoms that compose the molecule. IMFs are weaker than single, double or triple bonds. IMFs are strong enough to control physical properties such as boiling and melting points, vapor pressure, viscosity. IMFs as a group are referred to as van der Waals forces. Van der Waals forces: dipole-dipole interactions, hydrogen bonding. London dispersion forces. Dipole-dipole interactions. Molecules that have permanent dipoles are attracted to each other. Dipole-dipole interactions. The more polar the molecule, the higher is its boiling point. London dispersion forces. Helium has 2 electrons in a 1s orbital that repel each other. However, it does happen that they occasionally wind up on the same side of the atom. London dispersion forces. At that instant, the helium atom is polar, with an excess of electrons on the left side. London dispersion forces. Another helium nearby, then, would have a dipole induced in it. The electrons on the left side of helium become attracted to the dipole in He atom 1. London dispersion forces. London dispersion forces are attractions between an instantaneous dipole and an induced dipole. London dispersion forces. These forces are present in all molecules, whether they are polar or nonpolar. Only IMFs present in noble gases. The tendency of an electron cloud to distort in this way is called polarizability. 2 main factors affecting London forces. Molecular weight. London forces increase with increased MW. Number of electrons. Larger electron clouds are easier to polarize, which have a greater effect. Dipole-dipole interactions or dispersion forces. If 2 molecules are of comparable size and shape, dipole-dipole interactions will likely be the dominating force. If one molecule is much larger than another, dispersion forces will likely determine its physical properties. Boiling points. The nonpolar series, SNH4 to CH4, follow the expected trend. The polar series follows the trend from H2T through H2S, but water is quite an anomaly. Hydrogen bonding. The dipole-dipole interactions experienced when H is bonded to N, O, or F are unusually strong. We call these interactions hydrogen bonds.